The initial calculation of 1665 watts for the power absorbed by the load is correct. The equation power equals current times volts is only valid for a pure resistor. In this specific scenario, the load isn't a pure resistor. The reason for this is that it incorporates an electromotive force, often abbreviated as EMF, of 115 volts. This electromotive force has the effect of making the current lower than it would be if the load was just a pure resistor. Because the current is lower, the power that is dissipated by the load is also reduced. The correct equation to use for calculating power in this type of scenario is power equals E times I minus I squared times R, where P represents the power dissipated by the load, and it is measured in watts. E represents the voltage across the load, and it is measured in volts. I represents the current flowing through the load, and it is measured in amps. And R represents the resistance of the load, and it is measured in ohms. When we use this equation, we get power equals 115 volts times 15.87 amps minus 15.87 amps squared times 6,125 ohms. This then equals 1665 watts. Therefore, the power that is absorbed by the load is 1665 watts. To further clarify, let's delve into the components of a DC generator and how they interact to determine the power delivered to the load. A DC generator converts mechanical energy into electrical energy. This conversion relies on the principles of electromagnetic induction, specifically Faraday's law. The key components of a DC generator include the armature, field windings, commutator, and brushes. The armature is the rotating part of the generator where the electromotive force is induced. It consists of a coil of wire wound around a laminated iron core. The field windings create a magnetic field that interacts with the armature. These windings are typically located on the stator, which is the stationary part of the generator. The commutator is a mechanical rectifier that converts the alternating current generated in the armature into direct current at the output terminals. It consists of segments of copper that are connected to the armature windings. The brushes are stationary contacts that ride in the commutator, allowing current to flow from the armature to the external circuit. When the armature rotates within the magnetic field created by the field windings, an electromotive force is induced in the armature coil. The magnitude of this electromotive force is proportional to the speed of rotation, the strength of the magnetic field, and the number of turns in the armature coil. The induced electromotive force drives current through the armature circuit and the external load. The armature circuit has its own resistance, denoted as ρ, which includes the resistance of the armature winding and the resistance of the brushes. This armature resistance causes a voltage drop within the armature circuit, reducing the voltage available at the output terminals. The load connected to the output terminals draws current from the generator. The amount of current drawn depends on the load's resistance or impedance. In this case, the load is rated at 2 kilowatts at 115 volts. This means that the load is designed to dissipate 2 kilowatts of power when 115 volts is applied across it. However, in the given scenario, the generator's no load output voltage is 120 volts, and the armature resistance is 0.9 ohms. When the load is connected, the current drawn by the load causes a voltage drop across the armature resistance. This voltage drop reduces the voltage available at the load terminals. The equation used to calculate the current through the load, I equals V divided by ρ plus RL, takes into account the armature resistance and the load resistance. In this equation, E represents the generator's no-load output voltage, ρ represents the armature resistance, and RL represents the load resistance. The load resistance can be calculated using the formula RL equals volts squared divided by power, which gives 6,125 ohms. Substituting the values into the current equation, we get I equals 120 volts divided by 0.9 ohms plus 6,125 ohms, which equals 15.87 amps. This is the current flowing through the armature circuit and the load. Now, let's consider the power absorbed by the load. The initial calculation using P equals I squared times RL gives 1665 watts. This calculation is based on the assumption that the load is a pure resistor. However, as mentioned earlier, the load also includes an electromotive force of 115 volts. This electromotive force opposes the flow of current, reducing the power dissipated by the load. The correct equation to use in this case is P equals E times I minus A squared times R, where E is the voltage across the load. In this scenario, the voltage across the load is not simply 120 volts. It is actually 115 volts, as specified in the load rating. This is because the load is designed to operate at 115 volts. Substituting the values into the correct power equation, we get P equals 115 volts times 15.87 amps minus 15.87 amps squared times 6,600, 125 ohms, which equals 1665 watts. This result confirms the initial calculation and demonstrates that the power absorbed by the load is indeed 1665 watts. The discrepancy between the two power calculations arises because the equation P equals I times volts is only valid for a pure resistor. When the load includes an electromotive force, the current is reduced and the power dissipated is also reduced. The correct equation takes into account the electromotive force and provides an accurate calculation of the power absorbed by the load. In summary, the power absorbed by the load in this DC generator circuit is 1665 watts. The equation P equals I times volts is not directly applicable in this case because the load includes an electromotive force. The correct equation, P equals E times I minus A squared times R, provides an accurate calculation of the power absorbed by the load. Understanding the principles of electromagnetic induction, armature resistance, and load characteristics is crucial for accurately analyzing DC generator circuits and calculating power flow. It's important to note that in real-world scenarios, there would be losses within the generator which were not part of the problem statement and were specifically asked to be neglected. These losses include things like mechanical rotational losses due to friction in the bearings, hysteresis and eddy current losses in the armature core. Also, the resistance of the wiring in the field coils will dissipate electrical power. These would reduce the overall efficiency of the DC generator to values less than 100%. Finally, it's worthwhile to mention that there are various configurations of DC generators. The problem statement mentioned that the field coils were separately excited. This means that the field coils are not connected to the armature circuit, but instead are excited by a separate power source. Other configurations include shunt generators, series generators, and compound generators, each with its own characteristics and applications. In a shunt generator, the field windings are connected in parallel with the armature. This configuration provides a relatively constant output voltage, even when the load changes. In a series generator, the field windings are connected in series with the armature. This configuration provides a high starting torque, but the output voltage varies significantly with the load. A compound generator combines the features of both shunt and series generators. It has both shunt field windings and series field windings, allowing for compromise between voltage regulation and starting torque. The choice of generator configuration depends on the specific application requirements. Separately excited generators are often used in applications where precise voltage control is required. Shunt generators are commonly used in battery charging and lighting applications. Series generators are used in electric locomotives and other high-torque applications. Compound generators are used in a wide range of applications where both voltage regulation and starting torque are important. The calculations discussed in this example provide a foundational understanding of the principles governing DC generator operation. Applying these principles enables you to analyze and design DC generator circuits for various applications.